Next, the world's most advanced telescope took another leap forward this afternoon as its mirrors were unfolded 1 million miles from Earth. NASA's James Webb Observatory is the successor to the Hubble Space Telescope.
The third ever interstellar object observed from Earth, currently racing through our solar system. Now, astronomers have captured that moment live.
The gigantic eye of the James Webb Space Telescope locked onto 3Y Atlas on August 6, 2025, and what it revealed was far from the gentle, distant visitor many had expected. What showed up in the infrared was a comet-like body that was behaving, chemically and physically, in ways that stretched the imagination. This cosmic interloper, coming from beyond our solar system, is rewriting what we thought we knew about icy voyagers and perhaps even about the environments of other star systems. Before we start, smash the like and subscribe buttons for more updates. The discovery of 3I Atlas came on July 1, 2025 by the Survey Telescope Asteroid Terrestrial Impact Last Alert System Atlas in Chile. From the start, its orbit declared it interstellar. Its path was hyperbolic, unbound to the sun, and its speed and direction marked it as a traveler from another star system. Astronomers quickly trained ground-based and space telescopes on it as the realization dawned that this was only the third confirmed interstellar object to visit our neighborhood, after 2I/Borisov and 1I Oumuamua. What made 3I Atlas stand out was how bright it appeared, how large it might be, and how active it already seemed to be, even when still far from the sun. The Webb data would amplify those surprises. What Webb's instruments detected in the near-infrared spectrum was startling. A coma, the cloud of gas and dust around the nucleus, unusually rich in carbon dioxide compared to water. The ratio of CO2 to H2O is among the highest ever recorded for a comet-like body. Researchers suggest that 3Y Atlas may have formed near a CO2 ice line in its parent star system's protoplanetary disk, or it may have been exposed to intense radiation over eons, stripping away volatile water and leaving behind a more exotic composition. These findings hint that the birthplace of this object was very unlike the environment that formed the comets of our own solar system. Beyond chemistry, 3I Atlas's physical characteristics are also remarkable. The earlier estimate of its nucleus size was broad, but images from the Hubble Space Telescope placed upper limits in the few kilometer range. Some analysis suggests the nucleus could be at most 3.5 miles, 5.6 kilometers in diameter, though it might be significantly smaller. The object is traveling fast, exceeding 130,000 miles per hour, 210,000 km/h, as it blasts through our system on a hyperbolic trajectory. It will never return. It is merely passing through. What creates the sense of unease is that this interstellar object is doing things that typical comets do not. The high CO2 ratio indicates a formation region with very low temperatures or high radiation, one that may lie in the galactic thick disk or even near the Milky Way bulge. If the latter is true, then the object could be significantly older than the solar system itself, maybe 7-8 billion years old, making it possibly one of the oldest individual objects we have ever observed. That in itself is breathtaking, but the implications are even broader. If 3I Atlas formed in a radically different environment than our solar system, then the building blocks for planetary systems outside our own may be far more varied than previously thought. The assumption that comets in our solar system are representative of small icy bodies elsewhere may simply be wrong. Here is a body that seems to have originated in a place where water ice may have been rare or suppressed, but carbon dioxide ice was abundant, perhaps giving rise to very different histories of formation and evolution. The Webb data thus opens a window into the diversity of star system architectures, implying that the chemical reservoirs available for planets, their atmospheres, and maybe even for life might vary wildly from one stellar neighborhood to another. Equally profound is the possibility that this object, by virtue of its origin, composition, and trajectory, challenges our notion of the solar system's uniqueness. If material from other stars can wander into our system, carry with it a record of a totally different chemical and dynamical environment, then we aren't isolated in some safe bubble of uniform formation. We are part of a much larger, more dynamic galactic ecosystem where objects born in alien disks will eventually wander by, carrying the physical memory of places we will never visit. That means that future studies of interstellar visitors may become a way to sample the diversity of planetary systems without ever leaving Earth. Another facet that sends a chill is the sense that we only caught 3I Atlas at all by luck and at the last minute. The window of observation is short. Such an object will pass through and leave again, never to return. It reminds us how they slip through the system, how little chance we get to study them, and how much of the universe's story remains just out of reach. The Webb observations of its coma gave us unprecedented detail, but they may still be only scratching the surface of what such an object can tell us about the galaxy. The behavioral oddities don't stop at composition or speed. Its trajectory through the solar system lies almost exactly in the plane of the planets, a rarity for natural interstellar objects. Most interlopers would arrive from random angles, but this one has chosen a path that seems almost too neat. Its hyperbolic excess velocity and its tilt raise questions about how it was ejected from its home system, which stellar dynamics accelerated it to this speed, and whether such a path is entirely random. Was it flung out by a massive star cluster? Or did it receive a gravitational nudge that sent it on this precise entry track? The fact that we caught it at all suggests that objects like this may be more common than previously believed, but also that our detection systems are only now scratching the surface. Then there's the ill-defined question of what the unusual chemistry implies for potential habitability or for the origin of complex organics. If 3I Atlas is rich in carbon dioxide ice and poor in water, the environment that created it might have been extremely dry or subjected to a long era of radiation damage that desiccated it. That suggests that small bodies in some stellar systems may not carry the water we assume is necessary for life as we know it. If life elsewhere depends on water-rich comets seeding planets, then planetary systems that follow the pattern of 3Y Atlas's origin might be far less hospitable. In that sense, the object carries a silent but unsettling message about the variety of conditions under which planetary building blocks form, and by extension, about how narrow the path to life might sometimes be. The fact that Webb found CO2 dominance also suggests enhanced release of that gas as the body warmed, meaning that its outgassing behavior may be very different from that of solar system comets. That in turn means that if one were to rely on analogies from our own system to predict behavior of such interstellar visitors, one might be badly mistaken. Scientists now must adjust their models, reconsidering how volatile ices behave, how dust mantles age under galactic radiation, and how bodies traveling between star systems accumulate or retain primordial materials. The unexpected data from Webb is forcing a rethinking of assumptions made for decades. A further chilling implication is that, given its age and journey, 3I Atlas may bear physical features untouched for billions of years, essentially frozen relics from a different cosmic age. This means we are looking at a fossil from deep galactic history, not just a dusty snowball from the early solar system. It may hold signals of processes, radiation fields, or cosmic chemistry that no longer exist in our neighborhood. That kind of physical memory, preserved in a small body wandering between stars, is extraordinary, but also humbling. It emphasizes how little we know about the broader history of the galaxy, how many relics may be floating unseen, and how fleeting our windows to study them are. What Webb saw of 3I Atlas thus serves both as a scientific treasure trove and a wake-up call. It is a treasure trove because it delivers novel data, new chemistry, new physics of small bodies, and a direct sample of another system's materials. It is a wake-up call because it tells us our assumptions about interstellar visitors, about comet formation, about planetary system uniformity, and about how common our chemistry may be could all be flawed. The cold reality is that the universe may hold many more such objects, with compositions far stranger than we have yet imagined, and many may fly through our system undetected, leaving only a brief trace in our instruments if we are lucky. And if that weren't enough, there is the issue of what this means for detection and study of future interstellar objects. Webb's success in picking apart 3I Atlas's makeup shows the value of space-based infrared spectrographs, but it also highlights how quickly these opportunities can vanish. As 3I Atlas moves away, the data window narrows. It begs the question, are we prepared to detect, track, and study more such visitors with the speed they arrive? The implications ripple outward. New telescope missions, improved detection systems, and tighter coordination of space assets may become critical if we hope to capture the next deep space wanderer before it's gone forever. In sum, the James Webb Telescope's observations of 3I Atlas have revealed something deeply unsettling and thrilling at the same time. A cosmic traveler, ancient, alien in origin, chemically strange, and moving through our solar system with a serenity that belies its true nature. It is both a messenger from afar and a mirror held up to our own assumptions. What it tells us is that the universe is more varied, more surprising, and more unforgiving in its diversity than we have given it credit for. The silent march of the James Webb Space Telescope across the vast darkness culminated in one of its most compelling discoveries yet. A visitor named 3I Atlas, gliding through our solar system with secrets that chill and excite all at once. Its trajectory poetically unbound, its composition strange, its origin ancient. This interstellar wayfarer has become a messenger of things unseen, carrying the weight of cosmic history across light years into our observational sphere. In its revelation, our assumptions about cosmic objects, other star systems, and the diversity of planetary formation are upended. From the moment it was revealed that 3I Atlas's path was hyperbolic, unequivocally unbound to the sun, the sense of wonder shifted into something deeper, that we were looking not at a local comet, but at a relic of another system. Observations by Webb's near-infrared spectrograph revealed a coma dominated by carbon dioxide rather than water, a ratio among the highest ever recorded, and one that alone demands a rewriting of cometary expectations. That dominance of CO2 suggests either formation conditions radically different from those around our sun, or extraordinary processing over eons of exposure to cosmic radiation. The object reveals a chemistry alien to our solar system's standards, and along with that comes a cascade of implications. Consider for a moment the environment that must have birthed 3I Atlas. If it formed near the CO2 ice line in a protoplanetary disk of another star, the temperature, radiation, and chemical gradients would have been unfamiliar to our solar system's early history. Webb's data supports either an origin in that special zone, where CO2 freezes and water perhaps remains gaseous, or prolonged exposure to high-energy radiation, stripping away water ice and leaving carbon-rich ices behind. Such origins challenge our neat, tidy models of how comets form, that beyond a certain distance from the star, frozen reservoirs of water dominate and trace the story of a system's cold outskirts. 3. Atlas now shows us that some systems may instead have reservoirs rich in less common ices, and that those reservoirs might travel through the galaxy until intercepted by us. The implications for planetary formation are profound. In our own solar system, comets and that icy material are thought to have seeded planets with water, organics, and prebiotic chemistry. If 3I Atlas originates from a system where water ice was scarce or suppressed, then the story of habitability could be far more constrained than we imagined. Some star systems might bear abundant icy material. Others may yield bodies rich in exotic volatiles but poor in water. The very ingredients of life, as we know it, might differ radically from star to star. Through 3I Atlas, we see not just a visitor, but a signpost pointing to a wider chemical diversity in the galaxy than previously conceived. Another layer of disquiet lies in the age and provenance of this body. Based on its trajectory and velocity, scientists suggest that it may have originated in the thick disk of the Milky Way, a region older and more metal-poor than the thin disk where the sun resides. That hints at an age markedly older than the solar system itself, perhaps 7-8 billion years. To hold in one's mind a solid chunk of ancient ice or assorted ices, wandering through space for billions of years and landing, so to speak, in our observational field is humbling. It means we are catching a relic of galactic history, a time capsule that predates our planetary neighborhood and may carry evidence of cosmic environments long since vanished. And so we arrive at another chilling aspect, the rarity and transience of such moments. We glimpse 3I Atlas merely briefly, in its passage through our system with no possibility of capture, interception, or return. The observational window is narrow, the opportunities fleeting. We are reliant on the sharp vision of telescopes like Webb and ground observatories because such objects pass fast and vanish forever. This visitor moves at tens of kilometers per second, and will head back into interstellar space once again, knowing that we may never again see it, and that many others undoubtedly pass unseen, adds a poignant urgency to what we observe now. Within its behavior lies yet more strangeness. The fact that the CO2 to H2O ratio is so high means that standard thermal models of cometary outgassing may falter. If water ice is present but shielded by an insulating crust, then the warming by the sun might not reach the water until deeper layers, leaving CO2 and CO to dominate the observed coma. Webb's data hints at this possibility. A crust formed by sublimation in another system or by exposure to galactic cosmic rays over eons could insulate water ice, altering how we think comets evolve. The modification suggests that our solar system's comet models cannot simply be applied to interstellar objects without revision. This also raises questions about the physical nature of the nucleus. While size estimates remain uncertain, if the nucleus is several kilometers across, possibly bigger than previous interstellar objects, its history becomes even more daunting. Some observations indicate a size on the order of multi-kilometers. A large body means greater mass and structural integrity over time, meaning it could preserve deep layers of primordial material. That pushes the notion of 3I Atlas from being a small icy pebble to something more significant, a relic that may harbor layers of ice, dust, rock, and information about faraway origins. The environmental context of its journey through our solar system adds tension. As it approaches closer to the sun, the interplay of solar heating and its intrinsic properties cause increasingly dramatic outgassing. This in turn influences how dust and gas are released, how the coma expands, and how we observe it. The observation of a dominant CO2 coma suggests that as it warms, it reveals the internal story of where it came from. Each plume and dust stream, each spectral line, is a message from its parent system. The way it sheds material may differ entirely from comets we've studied, and that shift beckons us to think differently about small body evolution in cosmic space. Then there is the trajectory itself. The path of 3I Atlas is not randomly inclined, but lies in a region that catches our attention. Its approach is within the ecliptic plane of the solar system, at a phase and orientation that allowed our telescopes a relatively favorable view. That key alignment increased our ability to study it. If it had entered from a steep tilt or an obscure angle, we might have missed much of its subtle features. The fact that we can study it in such detail feels fortunate and ominous. There are likely many others that slip through without notice, but this one aligns well just in time. In combination, the chemistry, the origin, the age, the trajectory, and the physical size of 3I Atlas converge into a rather sobering message. We are still at the early stage of comprehending the diversity of small bodies in the galaxy. The solar system may be just one example among countless others, and our processes, our models, our assumptions may be built on a narrow sample set. With each interstellar visitor we track, that set inevitably broadens, and our sense of cosmic uniqueness is challenged. The discovery also forces our instruments and strategies to evolve. Webb's capability to detect and analyze this object emphasizes how essential infrared spectroscopy is to uncover the hidden chemistry of distant bodies. But it also warns that if we are not vigilant and prepared, we will miss future opportunities. Rapid follow-up, coordinated observations among ground and space instruments, and flexible scheduling become vital. The fleeting nature of passing objects means that delays or missed observations may erase the chance to glean key information, and in that sense, the Webb 3I Atlas observation stands as a model for what future interstellar encounters should trigger. Moreover, the story of 3I Atlas ripples out to the larger context of galactic ecology. These wandering bodies may represent the debris of planet-forming systems, catapulted into interstellar space by gravitational interactions or stellar evolution. They travel as cosmic messengers, carrying with them the histories of other worlds. Accepting this helps us view the solar system not as isolated, but as part of a larger dynamic galactic network of star systems, ejected fragments, and migrating small bodies. Every interstellar object we detect is another puzzle piece in the mosaic of our galaxy's evolution. In practical scientific terms, the data from Webb provides benchmarks and constraints for chemical models of ice lines, for radiation processing of small bodies, and for materials survival over extremely long timescales in space. That is powerful. If 3I Atlas retains ices of CO2 and CO when others might have lost them, then our timelines of icy retention, radiation damage, sublimation rates, and dust mantle formation must be re-examined. It demands recalibration of how we interpret cometary evidence from our own solar system and beyond. It also invites curiosity, and perhaps unease, about what else might be out there, completely unknown. If 3I Atlas shows such unexpected composition, perhaps some interstellar objects might harbor even more exotic ices, or structures we haven't yet imagined. The interstellar catalog may include objects that challenge the boundary between comet and asteroid, between icy body and processed relic, between biological habitability and barren wanderer. That possibility encourages humility in our cosmic perspective. Yet, despite the strangeness, there is something hopeful in the observation of 3I Atlas. It means that we, using the tools at our disposal, can peer into the formation conditions of other star systems. We hold in our telescopic embrace not just distant planets, not just stars, but the small bodies, the primordial debris of other systems. And those carry rich records. The data from this object allows scientists to test theories of planetary system formation. What star types eject what kinds of debris, what internal compositions survive ejection, how long they endure, and how they interact when they pass through another system. One cannot help but think of the philosophical dimension. We are watching material that traveled perhaps billions of years from a place we may never identify, across the gulf of space to visit us. It reminds us that every object has a story, and that the cosmic story is far richer and stranger than our textbooks often suggest. 3I Atlas is not just a comet. It is a messenger, a relic, a challenge to the notion that the solar system is representative. In our continuing observations of 3I Atlas, we will refine its size, its exact chemistry, its dust-to-gas ratios, and we may observe changes as it moves away. As it departs our system, it will take with it its history, leaving us only the imprint of what we managed to observe. That impermanence adds a poignancy. For a short time, our technology and curiosity align to catch a glimpse of a visitor from afar. Whether we ever see another such body soon is uncertain, but the record we build from this one will speak for centuries. Thus, more than an astronomical milestone, the Webb observations of 3Y Atlas represent a turning point in how we treat interstellar objects not as curiosities, but as fundamental cosmic probes. They hold the potential to inform everything from chemistry and planetary science to the broader question of life's prevalence in the universe. The strange chemistry of 3I Atlas, its dominance of carbon dioxide, suppressed water vapor, potentially ancient crust, and distant origin, pushes us to rethink our models and our place in the galaxy. With every passing month, as Webb and other observatories continue to monitor it, each new data point will refine our understanding of just how weird, how diverse, how unexpected the universe truly is. Its arrival alone was startling. Objects from outside the sun's sphere of influence are rare and fleeting. A small number of takings from other star systems have been recorded, and each has stirred vigorous debate. But 3I Atlas entered with a swagger, a speed and a path that clearly flagged its interstellar origin. That set the stage for a revelation that would be as unnerving as it is exciting. We were facing a true alien visitor, not of biological origin, but certainly of alien origin, and we were just beginning to understand the implications. One of the most unsettling aspects is how this visitor forces a reconsideration of the concept of small body populations across the galaxy. Standard models of comets, asteroids, and icy bodies in our solar system have been based on decades of study. Objects formed in the outer regions of a protoplanetary disk, rich in water, ice, and dust, gradually evolving under the influence of the sun and its planets. Here, however, is a body that didn't follow that script. Its composition and history betray an entirely different path. One that makes the solar system's small bodies look like a local subset of a much broader set of possibilities. At the heart of the shock lies composition. As observed by powerful telescopes including the Hubble Space Telescope and the James Webb Space Telescope, 3I Atlas boasts a chemical profile that does not neatly match the catalog of solar system comets. The ratio of frozen compounds, the outgassing behavior, the mix of volatiles, all of it suggests formation and evolutionary conditions that lie outside our precedent. It means the icy building blocks of planetary systems far beyond our own may not resemble those in our backyard, and that has profound implications for how we think about planets, moons, habitability, and chemical evolution. The trajectory of 3Y Atlas is also troubling in its implications. It didn't sneak past at the fringe of the sun's influence, but passed through regions where solar heating can modify its surface and volatiles. It zipped through at speeds so great the sun's gravity could not capture it. If it had arrived more gently, we might have thought it just another comet. Instead, we must treat it as an emissary of an alien planetary system. This means, when we study it, we are reading the record of somewhere else, and that record is weathered, jumbled, and complex. We must decode not just what it is doing now, but what it has done for eons, and that demands humility. If the solar system's icy bodies were our sample set, here we have an object that suggests we were sampling the most common kind of body, the most familiar kind of formation condition, and perhaps missing the stranger, less familiar majority. By contrast to our comets, 3I Atlas points at a diversity of small body populations that likely roam the galaxy. The way star systems eject material, the way protoplanetary disks freeze and sublimate, the way radiation and cosmic rays reshape bodies over billions of years. All of it becomes richer and more complicated when we incorporate this visitor. What this means for cosmochemistry is significant. For instance, if 3I Atlas formed in a region of a star's protoplanetary disk dominated by carbon monoxide or carbon dioxide ices rather than water, then the planetary building blocks in that system would be chemically different, and the planets that formed may have atmospheres, surfaces, and internal reservoirs that diverge from what we know. If water ice was suppressed or transformed or evolved into other compounds, then the raw ingredients for life, as we conceptualize them, may have been scarcer, or at least arranged differently. The record carried by this object tells us that habitability might vary not just in degree, but in kind. Another unsettling angle. These interstellar objects are not just passive wanderers, but may actively shape planetary formation processes. Recent research suggests that such bodies, originating outside a system, could be captured by protoplanetary disks of young stars and act as seed cores for planet formation. In the case of 3I Atlas, we are looking at the product of ejection. Somewhere a system ejected this body, and somewhere it may have influenced the architecture of that system before it was expelled. We are seeing the outbound stream of planetary system building, and it reminds us that stellar planetary systems are not isolated but interconnected. The galaxy is not a set of islands, but a network of material exchange. This dynamic has unsettling implications for our assumptions about isolation. We like to think of the solar system as a self-contained experiment, but this object tells us it is one node among many, and that material flows between systems. If that is true, then planetary formation, chemical enrichment, prebiotic chemistry, and the volumes of water or organics available may integrate contributions from outside the immediate system. That means the rarity of life, or the abundance thereof, may hinge on processes that inject or remove material between star systems, processes beyond simply the collapse of a protoplanetary disk. Moreover, the physical age of the object is deeply disturbing in its grandeur. If we estimate that it may be billions of years old, predating the formation of our sun, then we are looking at a relic of ancient galactic times. It has survived ejection, wandering, cosmic ray exposure, and interstellar radiation for eons. That longevity raises questions. What processes preserve such objects? What kind of shielding or structure allows volatile ices or layered dust to endure? It means that the small bodies we are familiar with may have far shorter survival times or different evolutionary paths than those interstellar relics. The fact that this object survived long enough to reach our neighborhood is itself a hint about the resilience of such bodies, but also about how rare and precious the opportunity is to study them. From a detection and observation standpoint, the arrival of 3I Atlas is a wake-up call. These objects zip through our system on trajectories that beg comparison to bullets and arrows rather than gentle loops. The rate of detection is low, our instrumentation is only recently becoming sensitive enough, and the windows to study them are narrow. With 3I Atlas, we are forced to recognize that we may only ever get one chance per object, and that each one may carry unique information never to be repeated. the urgency to develop survey capabilities, rapid response missions, and targeted spacecraft flybys becomes glaringly apparent. In passing, 3i Atlas admonishes us, we may not be ready for the next one, and we cannot rely solely on serendipity. In that urgency lies an uncomfortable truth. The universe is more unpredictable than we have assumed, and our preparedness is limited. The fact that this object appeared in our system now suggests that such wanderers may be more common than once thought, but also that many pass by unseen, ignored, or unrecoverably faint. Every unobserved visitor is a lost message, a missing data point in the galaxy's broader story. If we are to grasp the full narrative of small body populations, interstellar exchange, and planetary system diversity, we must become more vigilant, more capable, and less complacent. Furthermore, the notion of alien origin need not imply biological intent, but it does invite philosophical reflection. When material from other star systems drifts into ours, we are confronted with an ancient connectivity in the galaxy. We are reminded that the solar system is not isolated in time or space, that its formation, environment, and chemical inventory may owe to a broader galactic milieu. This visitor becomes a messenger of other systems, a physical shard of distant star-birth regions or orbital ejecta from alien disks. It demands that we think of ourselves not just in local context, but galactic context. The conclusion is unsettling. We are part of a galactic ecosystem, not simply a planetary system in solitude. As we watch 3i Atlas continue winding its way outward, the story it tells is still unfolding, but the stage it has set is clear. We find ourselves in the presence of a cosmic voyager whose presence rewrites storylines, whose chemistry challenges expectations, whose pathways traverse star systems, and whose very existence demands recalibration of our models. The implications cascade beyond astronomy into philosophy. How common are such objects? What do they carry? What do they say about the origin of small bodies, planets, atmospheres, and ultimately life? Are we seeing the tip of an iceberg of interstellar traffic or a rare apparition that reminds us how privileged we are to glimpse it? In contemplating 3i Atlas, we are forced to reckon with scale, spatially, temporally, and chemically. The object's age stretches beyond human timescales. Its journey spans stars and galactic neighborhoods, and its composition hints at formation environments alien to our own. That makes it both captivating and disquieting. Captivating because it offers a treasure trove of information. Disquieting because it underscores how much remains unknown, how our models may be incomplete, and how our sample of the universe is likely skewed. If you liked this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on what the James Webb Telescope just discovered about 3i Atlas? We want to hear from you. Thank you for watching and see you next time.